2013-14 URI Transportation Dissertation Award presented to Dr. Samuel Hammond. The title of his thesis. Congratulations.
Thank you.
Here we go.
If you have an iPhone, this is the time to take a picture, both of you. Okay, so you was?
Yeah.
Okay, then I'll go video. Okay, all right, how about that? Do you have anybody have iPhone? Nobody has iPhone? Okay. Thank you.
Wonderful.
Excellent. So, if you wish, you can read.
Okay, the best 2013-14 URI Transportation Dissertation Award presented to Dr. Samuel Hammond. The title of his thesis was The Effects of Additional Lane Length on Road About Delay. Congratulations.
Thank you.
Okay.
Here we go a long way, right? To the end.
If you have an iPhone, this is the time to take a picture, both of you. Okay, so you was?
Yeah.
Okay, then I'll go video. Okay, all right, how about that? Do you have anybody have iPhone? Nobody has iPhone? Okay. Thank you.
Wonderful.
Excellent. And then also the, if you don't mind, could you give me this one? This is the check.
Money.
Money.
Congratulations.
From the construction industry of Rhode Island. So this award is sponsored by construction industry of Rhode Island. So the executive director, Tim Skellon, supposed to be here, but he's not here yet. I guess he is in province still, okay? But you may write a letter or thank letter or whatever, something like that, right? Okay, great. Right. Congratulations again. Okay. Now, you may sit, okay? You may sit, okay? And then, because I don't want to hold the dean too long, okay? We want to continue over the second OD, and then you can make a presentation, right? Second gentleman who got, oh, by the way, before doing that, the Dr. Sam Harmon's major professor was Professor Chris Hunter. If you don't mind, could you stand up? Okay, okay, yeah. The best sweet gentleman in our, not only our college, in whole campus. Okay? All right, the second awardee will be Dr. A.J. Singh. Okay? You may come back here. And this is the Dr. A.J. Singh.
The best 2013-14 URI Transportation Dissertation Award is presented to Dr. A.J. Singh. The title of his thesis was Sustainable Pavement Management System for Low Volume Roads. Congratulations.
Thank you.
We need another call opportunity if anybody has iPhone. You have iPhone? Okay. I'm sure you are now the teaching at the University of Hartford. And you are making more money than the URI. Okay, you can come from the center, okay? Thank you, excellent, okay. And then there is a money part, okay, yeah.
This is also for you. Congratulations.
Thank you.
Okay.
Thank you.
Thank you. Thank you.
Thank you.
Excellent. Okay. So now the two gentlemen did excellent dissertation work, doctoral work. So aren't you curious what they did? Right? you're gonna hear from them what they did, okay? So I will introduce Dr. Sam Harmon, who is teaching, who is a faculty of Civil and Environmental Engineering at University of Harvard. Okay, great.
Good afternoon, everybody. So, as Dr. Lee said, I'm Dr. Samuel Hammond, and first of all, I'd like to thank Dr. Hunter, Dr. Thomas, and Dr. Lee for helping me with my dissertation. So, and I'm happy to be back at URI. So, for my dissertation, I worked on the effects of additional lane length on runabout delay, right? And so first, you might ask, why do we even have to do anything on runabout? From last year and previous years, Dr. Hunter has been presenting on like runabout, so you should know the importance of runabout. Safety-wise, they're very good. The studies have shown that they reduce crashes, total crashes by like 35%. And then the crashes that actually result in injury, a runabout, if you have a runabout compared to a signal line intersection, runabout reduce injuries that actually result in crashes that actually result in injuries by 75%. And also, you know, runabout, because vehicles are not actually stopping and waiting for a green light, they just have to yield, and if you have enough gap, you just enter the runabout. So it reduces emissions because of the delay reduction. And the average, it can accommodate large vehicles too, because we have like the radius that we use runabout, so larger vehicles can make easy turns. And one important thing that about runabout that I personally like is the fact that you don't have to use any equipment. Like signal line section, you need to have a cabinet, and the average cost about 20,000, depending on the number of legs. But runabout, you don't need any signal, you don't need any controller, you don't need any cabinet, and it saves like electricity. So I think the title for this year's forum is sustainability, right? So if you want to talk about any sustainable intersection, I think runabout is considering the fact that you don't need any electricity. In case we have a hurricane, any power outage, runabout can still operate. But with the signal line section, if there's any power outage, it's not going to operate. And because of the importance of runabout, as of last year, we have over 2,000. The first modern runabout that was built in the US was like 1990. And as of last year, we have about over 2,000 runabouts in the US. And in Rhode Island, we have 5 under operation. And according to one gentleman from DOT, we have about 14 under design. So as you can see, the number of runabouts are increasing in the US, right? But we don't have enough guidelines on how to design runabout. Most of the guidelines that we have, most transportation professionals, they refer to studies that have been done overseas. Like, I think the guideline that we use right now is based on like research that was done in the UK. And most of the time, if you transfer them, they don't necessarily work. So that's one problem with runabouts. And in the case too, like, you know, if you have a signal line section, right? At a point in time, you're going to have a demand exceeding capacity, right? So if you have a signal line section, usually as a transportation professional, you just go in, you know the parameters that you have to change, right? You know, okay, first of all, I can just work with the cycle length, the effective green time, but with runabouts, as of today, we don't have enough guidelines on how to modify an existing runabout in case demand exceed capacity. So just looking at this, this is the 20 runabout, right? So assuming we want to put a new, whatever, gas station, and studies have shown that you're going to add this amount of volume, right? And that's going to increase the delay and then the queue length at this runabout. I don't know, does anybody have any idea how to improve that in this case? So we have this runabout, right? And we want to improve it, like based on the fact that we're going to put a new gas station at the highlighted place where we have red. Does anybody have any idea how to, in case we want to improve this runabout due to the increase in volume? So that's the problem, right? In the US, we don't have much idea as to how to do that. Right now, we're just building roundabout, but in UK, they run into similar situation where they had to, actually the government had to fund that research where, because most of their roundabout had run into a situation where the demand had exceeded capacity, and they were just trying to find ways to improve them, and they came out with some of the, yes, Doctor.
What's wrong with additional lanes? Multi-lane?
Additional, so this is a double lane, assuming this is a double lane.
It's already double?
Yes, a double lane. We have a double lane roundabout. So I think in Dubai, right? Last I went to TRB, they were proposing putting a triple lane, right? And that increases the number of conflicts, and studies have shown that even though putting a triple lane is going to improve capacity, but you're still going to have safety issues. So that's a problem that we have, and that actually brought us into the objective of my research. So we wanted to investigate how the additional lane length in particular, right? Because studies have shown that the entry, for instance, is the most effective parameter. Either the length or the width of the lane, right? Is the most effective parameter that can improve the operation of a roundabout. But we don't have any studies that show how varying these parameters can improve the operation of a roundabout. So that was one of the objectives. And we also want to determine the exact length that can actually reduce delay. And also with this, knowing how the lengths operate, right? It will help transportation professionals design future roundabouts that can operate effectively.
Excuse me, you were talking about the gas station you want to put in there?
Yes, the gas station.
Well, don't put it in there. You could put 2 gas stations on either side, 2 small ones.
Yes.
But why, we have this thing going for, we want these big gas stations now with places where we can buy food and things like this. But maybe you don't want to have that there. Maybe.
Yeah, that's one good
Right.
alternative that you can use. But
Well, you put the gas station, make the gas station in view of the road, so that.
yes.
Right, instead of expanding the road, you just smaller gas station.
Yeah, so I mean, that's a good point to make. So we want to start that conversation, how to improve roundabouts, because in the near future, we're going to run into issues where the demand is going to exceed capacity. So it's a good starting point for future of roundabouts in the US. So we came up with 3 hypotheses, and that one was shorter additional lane length. If we want to find out if shorter additional lane length were effective in reducing delay, and the other one was if adjusting the lane on all, the additional lane length on all legs at the same time, and then the exit to, right, for all the legs. And then the other one was if you can just do for one leg and then not do it for the other legs too. So just to go, what we did was we came out with 2, we developed a hypothetical model and then an existing one. So with the hypothetical model, what we did was we just came out with a double lane roundabout and looked at and the fact that they should be aligned at 90 degrees. That's most of the time what roundabouts, usually, that's the goal, trying to align them at 90 degrees for the deflection, entry deflection. So we looked at those for the hypothetical model, and then we just put in different volumes to see how, if you vary the length, the additional lane length, right, how it's going to affect operation. So we use different volumes, and then from that, we're able to find out that as the length increases, delay would increase, but at a certain point, you wouldn't see that much, you wouldn't see a significant change in delay after a certain length. So just to confirm that, we also came out with an existing model, right? So that we could test our hypothetical model, the result that we're finding from the hypothetical model, if it's going to apply if we use an existing model too. So we came up with 2 models. One was the hypothetical, and then one was the existing one. And the existing one, we were able to find a roundabout that fit our hypothetical model, right? And that one is in Brattleboro in Vermont. So as you can see here, the legs are aligned at 90 degrees, and also it's a 2-lane roundabout, and we have additional lane length. And the fact that I think they did a study on 31 roundabouts in the US, and that was one of the roundabouts that they used. So we had data on that roundabout. So we realized that we could use that roundabout for that. So these are different scenarios that we did based on the fact that we want to look at just varying one additional, just the additional lane length on the approach, and then varying either the entry and then the exit lane length too. And then also we looked at whether if we just vary one, just the entry additional lane length, right, all around, and then just varying just one. And so, like I stated earlier, they did a study on 31 roundabouts in the US, right? And what they did was they collected data on all these roundabouts. So about 250 feet from the yield line, right, all the way upstream, they started collecting data like the delay at that point, and then also right at the entry, at the yield line, and then at the exit too, and then in the circulatory pathway. So these were, if we wanted to compare our hypothetical model with that, we had to model our hypothetical model so that like we collect data at these points so we could compare them and see how. So this is the hypothetical double lane roundabout that we used, and for the existing one too. So I went to Vermont and I measured how the additional lane length and then how it operated, and I also collected some data on the roundabout. And we used this software called Vissim, right? And the reason why we used that was the fact that roundabout is based on driver behavior, right? So it's more about somebody accepting a gap, unlike a signal light where everything is programmed and then you just wait for your green and if it's saturated. But a roundabout is more based on a driver behavior. So we had to come out with a software that could mimic that operation, right? So we found out Vissim was the best software to handle that roundabout, and studies have shown, a lot of studies on roundabout, they all use Vissim. So that was the software that we used to compare the delay, right? The delay data from the existing and then the hypothetical model. And this graph here shows like the calibration that we did in Vissim, right? And it's a very tedious work, but when you're doing the calibration, you just compare. So the one in red is a Vissim data, and the one in blue is a field data.
Maybe you can respond.
And in blue is a field data, right? So we just adjusted the data that we had in the in Vissim, right? Until these would match up. It was just a matter of looking at it and looking at the averages. So we just had to vary it, either the gaps, or at times too we had to adjust like the driving behavior in the software so that these could match up. And you could see there was some that they didn't really match up real good, but most of them matched up. So what we did was we had like, so when you start with the calibration, right, you're going to realize that at a point in time you're going to have the field data and then the Vissim data, right? So after a point in time they all be matching up. You realize that you wouldn't see much change in even varying all different parameters, right? You wouldn't see much change. So that was when we realized, okay, there's a point that we should actually stop with the calibration and go with whatever we have in the data. So we kept varying until we wouldn't see any change in the data comparing the field and then the field and the hypothetical model data. So this was the result that we had. We realized that, right, for the hypothetical model, this is what we found, right? So as we increase the length, delay would go down, and at a certain point, at a certain length, you wouldn't see that much change, right? It stayed, even though we're increasing the length, right? We had like 250, 350, you see the delay was almost the same, right? And was the same for speed too. So as we increase the length, speed increased, after certain length, like the speed stayed almost the same. So there wasn't any significant change in speed and then in the delay too. And comparing with the existing model too, we had the same result. Beyond a certain, like around 100. So this one we increased, we added 100 feet to the existing length, right? We added 200 feet to the existing length for the entry, right? And realized there wasn't that much change in the delay, even though we're increasing the length. So, testing our hypothesis, we found out that, yeah, shorter lanes were more effective in reducing delay. And also, if you want to effectively reduce delay, right, they have to be done concurrently. You just don't want to do just one leg and then leave the other legs to. If you vary the length, they all have to be done at the same time. And we also found out that like varying the exit additional lane length, right, was not that effective as varying the entry. So that was right. And in conclusion, we found out in general, delay increasing the length reduced delay, right? But at a certain point, you wouldn't see that much change in the delay. And at the same time, too, when you increase the length, right, speed increased, and that is an issue that we need to look at for future studies because runabout, the main reason why we came out with runabout was the fact that we want to improve safety, right? So looking at the fact, so to reduce safety, what they did was they wanted to reduce the speed. That's why they came out with a deflection at the entry, so it will slow vehicles down. But if you increasing the length, from this study we found out that increasing the length increase speed too. So that's one area that we could look at for future studies. And what I plan to do going forward is to just collect enough data on existing runabout in the US and come out with a database, right? So that and using that database, I can develop an empirical model that we can just use to understand how different. Right now we looked at the just the additional lane length, right? But I want to look at the diameter and then just different parameters, right? How they all affect operation. So going forward, that's what I would like to do. And I think when we have that database, we can easily understand how runabouts operate. And by doing that, we'll help transportation professionals meet the growing demand to, because nowadays everybody's talking about sustainability, right? And with a runabout, I think in the transportation field, that's the only, because the fact that we don't use any signalized, any equipment, and we don't have to worry about if it's any power outage, any Hurricane Sandy, runabout can still operate, right? So that's one area that going forward I would like to look at. All right. So any question?
So it's good time to ask any question and make any comment. Yes.
I just had one thing. I've heard that different states have different traffic regulations for roundabouts. So in our state, the person in the roundabout has the right of way. And someone mentioned to me one time that in another state, it's the opposite.
No, in the US, right, modern roundabouts, people in the circulatory pathway, they have the right of way. Unless, every state, unless it's just a rotary. So how roundabout started was, at first, that was the way roundabout was operated in the US, right? People that were actually entering had a right of way because it was not a roundabout. We call that a rotary.
Ah.
Okay, so with the roundabouts, you need to have a yield sign at the entry, and then vehicles entering, they have to yield to. But if it's a stop sign or whatever, at times, so if it's a modern roundabout, right, vehicles entering, they have to yield and look for enough gap before they enter the roundabout.
What about a rotary now? Are they still making rotaries?
Yeah, they still, I mean, some still exist. So that operation might still, like the one that you were talking about, where vehicles, yeah. So,
Ah.
yeah.
So we don't know, really, I mean,
For, in order to determine if it's a runabout, right, you have to be a yield sign at the entry, and
A
also,
yield.
yeah. So you have to, so a vehicle's entering have to yield before.
I see, so they're gonna tell me when I'm entering whether it's a rotary or a roundabout.
Yes.
Thank you very much.
You will.
Any other question, any comment? Okay, thank you, Dr. Harmon. The second presentation will be done by Dr. A.J. Singh, and the title of his talk today will be Sustainable Payment Management System for Cities and Towns. Okay? And then while he is ready for the presentation, I want to make a quick announcement. If you stay long enough, there will be social hour at 3:30 at Universe Club. So anybody find the time, you can join. Okay? All right, go ahead.
Good afternoon, everybody. My name is Ajay Singh, and Dr. Hammond's study was basically on traffic, and this study will be on materials and management, payment management systems. So the title is, as we can see here, Development of Sustainable Transportation Infrastructure Management System for a typical college campus. Since this is for low volume road, so that's why we took our university campus road network as a pilot study. So the study is based on URI network, road network. So this project, the problem statement for this project is that there is a problem of maintaining road and transportation infrastructure because road network is a big infrastructure, and all like economy of the state or even the federal government based on the road networks, of this. So we have to optimize the use of money, dollar. So that's why we have to keep on studying the payment management system. As we can see, the payments are deteriorating due to higher traffic and longer use also. And also less funding is available by the course of time. And also the material of the road construction is becoming costly day by day. So the basic problems which we find on the road are the distresses. So there are various types of distresses, out of which I can show you three major distresses which we can have in the road payment, which we see every day while driving or walking, and we don't recognize them. So like first of this is rutting. We see the depression along the longitudinal direction. There is one alligator cracking, and the third one is the pothole. We know this. So like this, there are like total 19 type of distresses. To solve the problem of the distresses in payment, we utilize payment management system. What is that? It is a tool that assists agencies in finding optimum strategies to keep the payment in the serviceable conditions with optimum resources, like human resources, labor resources and economic resources too. And this project was basically basically based on the sustainable criteria of transportation management system. So as I said, we selected URI network first in order to do our study. So as a network, So in order to start or in order to implement any payment management system on a network, the whole network has to be divided into
Yeah, that
yeah,
that works.
it's
Okay.
working now.
Yeah, that works.
So, like URI network was divided into two zones, first of all, which is divided by Route 138. As we know, there is Route 138. Some of you may don't know. It's just after, when we start into the URI entrance, then there is 138. So south of that is Zone 1, and south of Route 138 is Zone 2, and the north is Zone 1. And then zones were further divided into 22 branches, and those branches were further divided into sections. There are 47 sections. And then they are on the basis of their usage, we divide sections further into primary, secondary, and tertiary sections in order to have more analytical study.
Do we have definitions for those?
Yeah, we have, depending on the usage, I said. Like primary will be more used, like every time traffic, and the tertiary will be like very least usage. So, like we have example of Powerhouse Road, where 2 or 3 cars will go, or something like for parking, maybe something.
About sections on those?
Section is the representative part of the payment which will serve as the study area. I'll explain in further slides about that. So the data collection is done by this method. These are the guidelines from west to east and south to north. These are the primary directions for data collection. So we select some part of the road because we cannot survey the road. So while collecting data, we need to have some guidelines. And then I'll show you just in next slide. And there are some more guidelines like it should not be near to the intersection, and they should not be adjacent to. So I will show you this. Like here, we can see if this is a road, then we will have the sample units which are in sex on this, whatever. So can show you like this whole, from starting from here till here, this is a whole section, and this section will be divided into the sample units. This is not very big thing like rocket science, but it's like we have some guidelines that it should not be at the intersection, and they should not be adjacent to each other. Also, if you are finding the same characteristic, then you can skip that too. And these sample units will serve for the data collection. And the data will be in the form of 3 criteria. The type of the distress, as I saw, like pothole, rutting, whatever. There are 19 types of distresses. So one of them is the criteria is type. Then how much is the distress by quantity. Like you need to measure them according to the guidelines. And then comes the severity, how severe is the distress. So we have a booklet of APWA to select these type of criteria for finding the distresses. And these 3 criteria will be transformed into the Payment Condition Index, PCI, using a software, there are various softwares, which one of them is MicroPaver, which I use for this study. And after that, the distress will be scaled from 0 to 100. As we can see, PCI will be from like 0 will be fair, and then 100 will be good. As we can see in this like 100 PCI value road will be in the very good condition, like the best condition, and then comes 60. We can see a longitudinal crack, and then the alligator cracking we can see in the where the PCI is 5. after collecting data, after transferring into the software for condition analysis, then we will analyze the road payments for further in 3 phases. So in phase first, we will have the current payment condition. We will identify what is the condition of the payment first, like current condition. Then we will prioritize the sections, which sections is the most which is not serviceable or which have the best PCI value like 100 or 0. And then the corresponding preventive MNR cost requirement. MNR means maintenance and rehabilitation requirement will be quantified. In phase second, the payment deterioration trend for each family. So we will do regression analysis in order to find the deterioration curves, and the future condition analysis will also be calculated. Actually, we do like 10-year or 20-year future condition. How will the payment behave after certain time? So these are the characteristics of that software. And finally, we do economic analysis based on different maintenance and rehabilitation strategies. So we have different maintenance and rehabilitation strategies, which I will discuss just in a moment. This is the statistical analysis which I got from the software. It shows the payment of URI, how much is the fail, how much serious, how much is the good. So it's like a bar chart for that. And after analyzing our road, after inputting the data of URI, we got like 61 average condition PCI of the road. This is the condition at the last inspection of URI network, and that's the average value, 61. We have 2 prioritization methods, like worst first and the reverse prioritization method. So they have different characteristic how we can use which method. Some will be giving you more economic analysis, and other will be less. But I use one worst first method. So this is the chart for prioritization. As we can see, we can prioritize the roads section, like we can see here Alumni Road. Here having at that time of inspection having the least PCI of 2, so it was very deteriorated, and the best one was, I think, Davis Road, and the Graduate Village West was in good condition. Maybe they did some repair and rehabilitation at that time, but now it's not that much good. So this is the deterioration curve of a typical payment. As we can see here, y-axis shows the quality, how the quality of the payment will be there, and then the year, from 0 to 30 years, it's design time. And we see there is a sudden drop at one point where the value of the road repair and maintenance will be very high. The rate of repair will be very high. And before that it was something, then it will be fourth fold of that, 4 or 5 times. These are the maintenance and rehabilitation policies which we use for the payment maintenance. Localized stopgap, localized preventative, global preventative, and major. So these can be used depending on the condition of the payment, and based on the critical PCI, like what is the critical PCI of that class of payment, and then what is your current. So, and their definition is based on this. The first one is localized stopgap, to keep the payment in safe and operational condition, and it's used in high severity distresses that could be safety hazard, like very bad condition of the payment. And then localized is same thing to slow down the rate of deterioration, and various pothole patching or crack sealing will be used in this. Global, this is same, but if you are using globally, depending on the availability of the fund. And the major is reconstruction of that whole section or whole study area under construction, under consideration. So PMS has various parts to study. So maintenance was that, and in the project level, I did also the design part of that. So how to evaluate the performance of payment? How the payment is performing based on the material, structural, and we do climate also, but we didn't do climate in this study because it's very extensive study. So there are some agencies which has been doing various other studies, and they are basically based on the old specification. But in my study, I just finished. I used SuperPave and the advanced technologies, and I performed various tests on asphalt as well as asphalt binder as well as aggregate. Like I will give you just like DSR, dynamic shear rheometer test to determine the rheological properties of asphalt. This will give you how the asphalt will behave with the temperature as well as with the traffic loading also. And then the bending beam rheometer test for thermal cracking, like because due to the change in temperature, like diurnal change, which is day and night change, and also like a monthly change of the temperature, the payment, flexible payment, which is asphalt payment, has the tendency to shrink or expand. So it will form cracks due to which. So we need to do these tests on that. This is bending beam rheometer. I'm not going into detail of that, just, and then comes the ABCD, that's called asphalt binder cracking device test. So we just have cracking test. Some tests were, okay, then the asphalt concrete was designed on the basis of performance grading system of SuperPave. So we have the SuperPave gyratory compactor. These are the samples which were fabricated in order to obtain this OBC, optimum binder content of the mix. This is one other performance test of the asphalt binder concrete. This is a rutting test. This was done by APA, asphalt payment analyzer. There are some more tests which I did for fatigue cracking also. And this test is IDT, indirect tensile test for low temperature cracking. This was done with the install machine. And these are the results. It just says that I used hot mix asphalt, and I also compared CIR with that. That's cold in place recycled material in order to have the sustainable material. And this result showing that CIR is more ductile than the HMA in this case. As we can see, the creep compliance is more here. Then based on the condition history, the future condition analysis of the payments were developed. Then also budget analysis for the URI network was obtained. I used micropaver software for this, using their own, like sometimes default value, sometimes I use the other towns' rates for policies. I considered inflation rate also, and if there is some budget constraint trend, which is always there in the town cities. So I also use that one. And these are the four major, four MNR, maintenance and rehabilitation policies. And I compared the amount which we are getting out of these four policies. Also, in URI network, since this is very small network, I also implemented GIS application too. I could have done more, but I tried to use our GPS, which is in civil engineering department, but that was not giving me proper coordinates of the URI. So I used RIGIS, Rhode Island GIS data, in order to get this base map of URI Kingston URI network, payment network, as we can see here. This is showing us the spread of the sections based on their serviceability, like primary, where are they by color coding, secondary, tertiary. And I also did, using GIS, the age of the payments. As you can see, the thickest line is the oldest payment. Like there's 50 years. Most of the payments are 50 years. These are the age of construction and age at the last inspection. Then the condition of the payment at every 10 years interval. Since we are collecting data since 1986, every year the URI student, undergraduate student, they go in the field and collect the data of all URI network, payment distress data, and they put into a report, and then we use for study of payment management system. So this is 86 data. As we can see, how many payments are in good and how many payments are in the failed conditions, as you can see here, according to the color codings. In order to just compare one of these, as you can see, in 95 and 2005, the condition of the URI payment network, this section has been changed into this one, and because of some rehabilitation was done in between. Okay, so in conclusion, a sustainable payment management system of URI Kingston campus was developed using past 13 years data in this particular project. Prioritization was done based on the first method, and the PCI predictions for prediction models were generated for 3 families. And then, as I said, like 5% inflation rate I use, and with the budget constraint of 300,000 per year for this study. In the study of sustainable material like CIR or WMA, war mix asphalt, I considered these two as the additional MNR strategies to study a sustainable payment management system. GIS, since it's a very good tool to analyze any payment very fast, so I use GIS, and which was giving me very relevant result very fast. And it can be used for big cities and town or state level road network. And most of the agencies are using this now. So in recommendation, we have like URI facility office can use this study. The data collection should be continuous, and in order to have the consistent results, the collection should be very frequent, and PMS should be incorporated with the other performance parameters like structural capacity and IRI, International Roughness Index, like smoothness and smoothness criteria of the pavement. Also, climate also, which I didn't include in this. More studies need to be done on the recycled pavement materials. So I use only CIR extensively, Warmix a little bit. So there can be some more recycled material like even plastic or crumb rubber, which we can use in this. In order to have the visual interpretation of the results, as I said, GIS application have to be introduced in large scale. For bigger network, like we can use LiDAR data too. That's one, in order to monitor the pavement conditions. And it is hoped that this study will assist the campus and other agencies which have the similar characteristics of URI Kingston, and it can be used for bigger network too. Thank you. Any question, please?
Yes. Did you say that pavement is better right now around campus than it was in 1996?
It has been rehabilitating since then, and it has been deteriorating also. So we were comparing the different years' results.
Okay.
So depending on based on our collected data.
Okay. So 2005, how about 2000?
I can have that too.
10, 13? Okay.
I have that. Actually, I don't know where I skipped that in this PowerPoint
I
presentation.
just feel like it's bad.
Yes.
Somewhere at the University of New Hampshire, and what I've experienced here, I've not seen over there at all.
Yeah, this.
And I'm wondering what can be done. That's really what's real
Yeah,
bad. Also, it seems to depend on the time of the year. I've seen speed bump get created at some intersections here.
yeah.
Let's be tough, and I don't know what. It's in the spring. It's just pavement itself transforms itself all over campus.
Yeah, and it
So
depends.
when do you collect your data?
In spring semester mostly. Yes.
So you have a record of those speed bumps?
Yes, we have. Yeah. If they were created at that time, not before that, then we have all data of speed bumps, even the drains also, side drains and shoulders too.
So what can be done so we have a decent,
It's a study like how our payments are behaving and what are the conditions of the payment, how much amount we require to implement our payment management system or rehabilitate them. So it's like a budget study.
have you communicated your results to anybody on campus?
I tried, yes.
You tried?
Yes.
In one of, I noticed in one of his recommendation, if any of you can write $300,000 check,
Okay.
Then-
You think we'd be better?
he said it requires $300,000 to have better road?
Yeah,
Like that?
for 1 year,
Yeah.
for all.
Are you still talking about maintenance, or can we get rid of it all?
Yeah,
Has to be the case that
it was,
something has to go.
it was like $2 million something. If you want to implement major M&R policy, like
The-
reconstruction of the top layer.
That's 2 million?
Yeah, I think so.
I suggested AJ to communicate URI facility office, if not president or something like that. But he did not get any luck to get a response. So this university is becoming interesting university. They are ignoring students. So unfortunately, he had like a limitation. That's what I found. You may go to excuse me, you may go to your bio, right? Huh?
What?
Okay. All right, it's okay. You can look at the door. There's change of the classroom. You can go out.
No, I know, I just work.
She's on my crew.
Oh, I'm sorry. Oh, thank you. Sorry about that.
I have a question.
Yeah.
I'm interested in the same thing that you are, only maybe a little more specifically, because I'm interested in the patchwork that's being done. And something I think you could do is that you could check the university's specifications for the patchwork, and also see how they have some people come back and check the patchwork if it's been done properly. And then you might begin to understand that these bad roads affect the front end alignment of our cars. And as a faculty person, you might go through the union and say, listen, we want you to change your specifications so that we get better roads.
Okay.
That's
Good.
okay.
Good suggestion, thank you.
Good suggestion. Thank you, AJ. Okay. We have at least 3 more presentations, so we want to try to keep on track. Okay. But he'll be available, so you can have a further discussion. Okay. Next will be Professor Yang will come forward. Professor Yang should leave before 3, so we'll change order. So he will talk about AJ.
Could you
help with
give
the-
a help?
The topic of his talk will be measurement of adhesion properties between top coat paint and metallized galvanized steel with the surface energy measurement equipment. So it's interesting topic. So he has conducted a research program for New England Transportation Consortium, NETC. NETC is the consortium of 6 New England State DOT. What they are doing will be they are pooling $500,000 every year. So 500 times 6 states will be $300,000. And then they are sending out the RFP every year. So Professor Yang and I applied one, and then we received one, and then we conducted research program about painting. Here is Professor Yang.
Trick or treat. Okay. Yeah, as a faculty in art and science, when I dress up to the classroom and the students ask, what happened? I said, Halloween.
I see.
Why do you dress?
That's your Halloween dress.
Right. So, it's a pleasure for me to talk again, and some of you might have already heard some part of these results, but this is, I think this is finally, we finished 500 pages report. This will be the final presentation, and as Dr. Lee mentioned that this is a supporter for the New England Transportation Consortium, and there's a map of the states involved, and we are acknowledging there is a technical committee which guide us through this process. Is a research and also personally is a learning experience for me. And we also want to thank some people who outside the technical committee and help us out from the Massachusetts Highway Department and Rhode Island DOT, Mike Hewen and Michael Sock, and Richard Brown from the Chemical Engineering Department of University. And here, this is a picture of the opening day of this highway, that bridge which you probably all passed through. And now this is cars running on there. And this frame structure is steel with the zinc coating on the bare steel, and then on top is coated with 2 layers of paint, which are the first layer is a epoxy. In the specification is usually called an intermediate layer, and then a urethane top layer. And so this is a urethane on the top, epoxy, and zinc metal, and then underneath is a steel. And why is that called an intermediate? It's because there is a qualified list called a NEP code. And the NEP code originally was designed for a bare steel and painted on a what they call a primer. Is a zinc primer. What it is really a epoxy paint with more than 50% mass of zinc metal powder, and that painted on steel. The reason you always want a zinc is because prevent corrosion. All right. So now at the offset, there are several questions because on that time there is one problem is that you frequently see a peeled off paint on the roadside. And a lot of times people blame that the paint is difficult to adhere on zinc surface. Okay, is it the question is although it's good for preventing corrosion, is it bad for paint adhesion? And that was not clear. And also, at onset, like these, Rhode Island DOT is advocating using so-called a thermal spray zinc. And most other states use galvanized steel. Okay, so what is there any preference on those? And then thirdly is in the industry there is always a conventional wisdom saying that okay, if the paint doesn't wet the surface, it doesn't adhere very well. Okay, so that's that's true. And the question is, it has not been studied that there is, if you use a certain measure of the paint wetting, which is the contact angle measurement of a liquid paint droplets on the surface, if you use that, does that correlate with the strength of the adhesion? Okay, so. Now, this is a picture of this is a galvanizing, and as this a thermal spray for applying zinc metal on the steel surface. Then this galvanizing is called a hot dip galvanizing. Is a molten zinc and with the steel pipes dipped in. And when I saw those in the factory, it needed to have a remote operation to do that. It's quite hazardous. And there is another method is vaporizing the zinc. It's not really, I shouldn't say vaporizing. It's a molten zinc and sprayed onto the metal surface. The difference here is these when you first galvanize it, the surface is smooth, and the thermal sprayed surface is rough because the particles immediately, instantaneously solidify into small micron-sized particles, and they aggregate on the surface. It's not smooth. Okay, But in the industry, it's known that the surface profiling really is roughening is important. And in the industry, what they say is that you need to transform this smooth surface into a rough surface, so the paint has a bite in that. That's speaking from their experience. Okay, so we are investigating in that too. So what it is, there are 3 different ways of producing roughened zinc surface, and it's a foregone conclusion that if you don't roughen it, the paint is going to peel off. That happens. The Rhode Island DOT told me that is when Jamestown Bridge handrail, which was painted the first week, the second week, you can take one piece and peel the whole rail off, and they rejected that those paint job. So what we have is a galvanized and use a so-called sweep blast. The sweep blast is blasting with gently with the right kind of force to make it rough. And the reason is that if you go too brute force, then it's going to blast off all the zinc layer you have, and left with bare steel. Okay, so that there is a technique or the industrial standard that produce that, and then you paint with epoxy and polyurethane. And another way is galvanizing and then mechanical profiling. The mechanical profiling is have like a sanding machine, and make the surface mechanically have the grooves in there. The third one is the thermal spray. Okay, that is naturally smooth, and this is a URI. This is other than road. There are some paint which peels off, and that is, you can see inside is the galvanized zinc, and this is a frequent site. So there is a concern that is that inherently different. Okay, here this shows this is galvanized but mechanically roughened, and this one is thermal spray. So you can see that this is porous, and this is initially shiny, but it has grooves in there. So questions again. What we ask is 4 questions. One is this is called a duplex painting, okay, and a zinc-rich primer, and we use these as a test panel. This is a control to compare. Okay, now the zinc-rich primer, and I think my battery might is this.
Yeah, that's the.
Oh, okay.
Yeah.
How do I?
Batteries out.
It's out too. Okay, mine is weak. Okay, I will just intermittently point. So, as we said, is the question is, because we see so many peeling off, is that an inherent problem? Okay, and we compare with this approved zinc-rich primer, which we have many years of experience. Then these 3 kind of zinc surface, which one is better? And then we say that well, if we use look at the paint wetting by the contact angle, are different paints give you, and on different surface give you different contact angle? That meaning is a different wetting property. And are they different? And it's, on the onset, it's not necessarily different because they all, the major content is an organic solvent, and they use the same ketone, like similar to the nail polish solvent. And if that dominates, then there's no difference. And the fourth is if there is a difference, can you use that difference as a predictor for adhesion? Okay, so this is the test panel we are doing. Let me, okay. So, the test method, this is called a pull-off test, is the dried paint is being glued on, and there is a device to pull it off, and we measure how much pressure in terms of a PSI in there. And then there is a S-cut tape test for the adhesion strength. And then on the other side, it is same, before it painted, the freshly prepared the liquid paint is being dropped on the surface, and we measure the contact angle with the surface as a function of time. Okay, so well, this is just showing that there is a lot of parameters that we control or test, and a lot of panels, and the equipments are, this is the test panels are here, and then this is a pull-off test equipment, and this is on the right is the surface tension measurement. Okay, so I'm just going into the answer to the questions. Anyone interested in the details, send me an email. I will send you this report, which is have all the details in there. And the question one is it inherently inferior in terms of adhesion? What we found is no. It's first of all if it's done properly, all different types is past the minimum requirement, 600 psi, and the duplex is comparable, with a good NEPCO list standard. These are the industry participated in the test program and produced. The second question is paint adhesion in a different roughened surface. Is there any preference? And what we find is that there are contact angles are different for different pairs, and the pull-off strength is different from different pairs. But you can always find one pair of each of a type of this zinc surface, and which will perform extraordinarily good. It's meaning that in the pull-off strength is above 2,500 psi. Remember that the passing grade is 600. Okay, so none of those. But however, what we discovered, the pairing is important. Which paint applying to which surface is important. Okay, so now the third question is that if, as we said that at the outset, although the industrial, the wisdom in the trade is saying that if you don't wet, you don't get adhesion. but it's not obvious that when we measure the contact angle, it will be different because it's largely the same solvent. And what it turns out is that with the right formulation, and there is a difference. You have a pretty wide range of contact angle and the behavior as a function of a time. I don't have a time to go through those details, but what it is now, if you see this is different pairs has the pull-off strength are different and the contact angle are different, but if you plot it, you see a correlation. It's not a perfect correlation, but reasonably strong. Okay, so in other words, the contact angle is a good proxy for wetting property. And the low contact angle, that is spreading out the paint, and you get a good higher pull-off strength. And so there is a correlation, and this implies that you do have, if you want to know that if you wanted to have this 2,000 psi pull-off strength, maybe you need it. You can do a test beforehand that whether the wet paint droplets is spreading well, and this could save a lot of money if you, instead of having it all painted and then peel off. Okay, so what we are, well, this is a example of our one of these thermal spray surface, and it's what we come up with a recommendation that is for the thermal spray the surface you should use a sealer. The sealer spreads very quickly. You see that these droplets, when it comes into contact with the surface, and in 6 seconds it's all disappeared, spread out, and the time data is at. And indeed, when that happens, you have a very strong adhesion. Okay, so the conclusion is that adhesion strength is strong, and the duplex industry like to say that it's as good and as the traditional, and it burns out. You can get a performance as good as the Nepcoat list. And there is a correlation of contact angle with the strength, and potentially you can make use of that kind of a thing for pretest to select a match of a surface and the paint. And for the thermal sprayed surface and a low viscosity sealer is recommended. And so I think that's it.
Yes.
I would like to entertain any questions.
Yeah.
Oh,
I just have a very short question. What is the best angle for, the best contact angle for adhesion?
Okay, yeah, it depends on the surface. For a given surface, you use a different paint. The lowest contact angle is the best. Okay, and however, that with one surface like these glass roughened galvanized surface, the contact angle never gets to zero. And but however, it's the lowest contact angle in the range like a 20, 30 degree, and that perform as well as the thermal spray, which gets you 0 degree, and it's in terms of pull-off strength, it's the same. So basically, for a given surface, you want the lowest contact angle, right? But you cannot say that the one type, the angle is lower than the other, is necessarily better.
Okay, thank you, Professor Yang.
Thank you.
Next presentation will be done by Professor Zhang from Department of Mechanical Engineering. The tentative topic of his presentation will be highway pavement thermal energy harvesting. So, as you know, we had a challenge about the energy. So the engineer is the problem solver.
Here.
So the energy becomes
Which
problem.
one?
So we try to solve that problem. So the Professor Zhang has a very interesting, unique approach to harvest energy.
Where's your laser? Is this one?
That is not giving. Mine is weak.
Yeah, this
But
one.
it works?
Yeah.
Okay, good.
Okay.
The topic of my presentation is methods of the highway thermal energy harvesting. Okay, this is the outline of my talk, and basically I'm talking.
Could you press that
Okay.
the mic make larger? Yeah. No,
think there's
no, the screen there.
This one.
That's it. Thank you.
Okay. I will talk about 3 topics. First, a basic introduction, then talk about the new methods, potential new methods of highway thermal energy harvesting. And those are the 4 different methods. Talk about energy harvesting, potential methods of use the pulsating flows, and also talk about absorption methods. And the last 2 talk about use the natural energy for the highway applications. And next we have time loss. I will briefly go through the potential optimization method needed to design those harvesting device. So that's a definition of energy harvesting highways, means that the energy is captured, stored, and applied it relate to the highway system. Traditionally, there's a typical highway energy harvesting. First is direct solar power. We can see these solar panels listed along the highways. Those are typical methods. Also wind energy. We've seen the wind turbine, which is installed near along the highways. That's also traditional methods. And the third also popular method is kinetic energy, which is you build some small device along the highways. When the car passed, it will generate the pressure on those small devices, then can generate electricity. The fourth one is less popular, but we do see some, is try to collect the energy from the wireless energy. Okay, those are a small sensor applied typically. So collect some wireless radio frequency energy to drive those sensors. But there's also the fifth one, pavement thermal energy, and which is very huge. Potentially it's going to be very huge, but also it's not that popular as now. Okay, so the potentials of this pavement thermal energy, and this is a picture, I believe it's near Shanghai, it's about last year, and show the time sequence. So you put, basically the pavement heat can be used to cook the meat. So this is the second, the meat the bacon start to change the color. And this is about 1/2 or later, so this is they cooked it. And show this how high the temperature is. And this is another picture. And this picture, okay, is not directly related to highway, just say the surroundings near the highway, the temperature is also very high. So this plastic post have been deformed, so the surrounding air temperature is very high. And this is another example, and see if you can enlarge that. Okay, it's a strange picture there, and looks like car being vandalized, have been punched a hole on the tire. Actually, this is not somebody did work. Actually, it's because of heat on the pavement, and so for some reason the tire was broken, particular tire. So that's also one of the strange picture in the internet. Let's see. This one?
Yeah.
Okay, those are the trade-offs of the thermal energy harvesting. Advantages is pretty obvious: free and enormous heating source, and easier to installation. Don't need really need high tech, and the low maintenance, and environmental friendly. And the disadvantages also pretty obvious. First is low quality heat, and the temperature, the hot water available extracted from this device is relatively low, and it's about high temperature is about 60, 70 degrees C. Okay, practical temperature there. The second disadvantage is most deadly disadvantages is unstable heat source, because if you want to build a power plant, you really want a stable heat source. Okay, the heat quality can be lower than this highway. Example of this is that the ocean, people use the green energy. One of these that use the temperature difference of the ocean temperature at the ocean surface, and about 200 meters deep depth there, there's about 20-30 degree of the water temperature difference. They use that 20 or 30 degree difference to generate electricity. Okay, there's a prototype of the power plant was built. Okay, it was reported, but the problem is that it's unstable. That's is going to be problematic. Okay, several days without raining days, then all the heat are gone. You don't have any heat. The third one is a high upfront cost, and also the last one is less mature technology. Here, it's not technology is mature, but the things that very few application. Okay, that's called less mature. So here is some potential methods. So I've divided into first potential method. The other group is feasible method. So this is the potential method. One of the potential methods is that can we use the energy harvesting from the heat-induced flows? Okay. So the mechanism is that because of an unsteady bubble, we call two-phase flow, and it will generate dynamic pressure variations and dynamic temperature variations. Can we harvest energy from those devices? Okay. So here is the concept of the pulsating heat pipes. And this was a pattern. Was about initially it's invented by a Russian, but the patent expired in early 1990s, and so people now rushed up to try to do, because the patent was expired and not continuing. So all the people in the heat transfer field try to rush to this concept, try to see if there's a practical applications, and particularly in electronics cooling. And so here in this particular picture, we see this is hot side and blue is cold side. And so hot side is a high temperature, so you try to evaporate these liquids, generate bubbles and the two-phase flow. Then two-phase flow, because of oscillating, because of the high pressure, will cool down, goes up, cool down by this heat sink, lower temperature. And this process can happen naturally without pump. And the fluid can naturally circulating within these loops. And so basically you have the heat will transfer from high temperature to low temperature. And the flow can be automatically driven. And so here is a device we try to build. And let me give you direct, let's say if we can use a video. Okay, these are the things we built, and this is a brown material. This is a epoxy here. And it's really a little rough, but basically you can see the heating and the cooling area. And this is just starting heating, and you see the bubbles, okay, in this different color start moving. And during one period of time, this bubble is moving very fast. I just stop right away. Go back to. This didn't work. Okay, this working fluid is water. Okay, in this case, just real water. Of course, you can use a different kind of fluids, and if you want to have a lower temperature for water, you probably need to vacuum a little bit, which is potentially could be the trouble in the highway system. You really don't want to vacuum, but you have to use different fluids. And also, there's other things that there's a filling ratio. And this filling ratio is how much liquid you fill into those tubes. Okay, that's also a very important factor right there. So there's lots of variables right here, and this is we did some experiments. That's a typical experimental measurement, and this is average temperature over the time. And in this particular case, if you look at here, the temperature we do is around 80 degrees. And some is closer to 100, and the lower cooling temperature is a tape water, is about 20 degrees. So the temperature difference is about 60, 70 degrees. This is the actual measurement. And we can see that the temperature really fluctuated instantaneously. Okay, the fluctuation range could be 30, 20 degrees, very huge. And so this is just typical experiment measurement. So here is a proposed mechanism. Let's say how we can harvesting this part of energy. Okay, one method, the concept here is that first, can we use these piezoelectrical PZT elements just simply embedded into the flow? Okay. So as these bubbles fluctuated, pressure fluctuated, this is beams also fluctuated, which will generate electricity right away. Okay, so the first concept. The second concept, because of temperature fluctuation, instantaneous temperature changes, the temperature changes because of the bubble burst. Okay, certain burst, you have dry vapor and high liquid, so there's a temperature jump, a very short time. And how about we can also use a seeback and seeback elements, which is basically translate the temperature difference into the electricity, generate the voltage. Okay, so that's the second method. The third potential method is that we can automatically pump in the flow, okay? Because this is oscillating flow, but if we put a flow rectifier elements, then we can let the flow go in one particular directions. So basically, you're pumping the highway flow. You don't need a pump. Automatically force flow into one particular directions. So here is a concept. Let's say this is a typical, we call flow pumping, and use nozzle diffuser elements. So here is a diaphragm going up and down, generate the pressure fluctuations. In particular, in this case, okay, the diaphragm is going up, so generate the negative pressure inside the chamber. So flow rush to the chamber because of negative pressure. However, flow relatively easier to flow as a nozzle, as a diffuser, and it's a little bit difficult to flow in as a nozzle. So more flow from right to the left, to the middle, and less from the left side. So now this diaphragm is moving down and generate positive pressure, and flow is going to be pushed out again because this is a diffuser, and more flow come out, less flow come to the right direction. So a simple cycle fluctuated, you will find that more flow going to the left, going from right to the left. Okay, so this we call the rectifier elements embedded in a pipe. So in this way, we can pump in the flow without pipe. That could be potentially save the power of the pump. We don't need a big pump now. Okay, so this is a first method. Now let's talk about second method. Second method is we try to use the heat, use absorption refrigeration. Okay, instead of electricity run, let's use the heat absorption refrigeration units, which is powered by the heat. Okay, this is a traditional, it's not a new method. And in the old days, we sometimes don't have electricity, but we can use a heating oil to power the refrigerator. And we see this kind of things in the market in the older time. Now we can pick up this technology to use that to generate cooling during the summer time. But one of the problem is that typically, okay, the temperature, heating temperature, have to be greater than 95. Even the green energy, which is energy, which is water ejected from the power plant, typically is around 195 degrees. Okay, but the highway water typically is very low. Let's say less than 65 degrees C. So the quality of water is really low. It's not good enough to run even those heat-powered refrigeration. So now we proposed solution. Okay, two solutions we can do. First, we can use two-stage absorption. One is use the first type things without go to details. Okay, basically we can use absorption heat pipe. Okay, this is relatively new technology, which is about 10 years ago was proposed. We can use this absorption heat pipe, basically 65 water come in and use the heat to further heat to the 95. Okay, although the water heating source only around 60, but use the heat pipe to enhance the hot water output to 95. Then use 95 the water, runs the regular air conditioning, and after that you can provide cooling water to buildings. Meanwhile, cooling building also have the heated water, and this is the heated water for the shower application. Return water 15 degrees, okay, still can used into the absorption air conditioning. So that's the one method. So basically, the concept is that we'll propose a new heat pump in front of the regular absorption refrigeration. The other problem I have to overcome is unstable heating source. Okay, unstable heating, particularly at nighttime, there's no heat. Then how do you power this refrigeration? So our solution, okay, this is the typical cost about those things, and let's give some numbers. And one of the proposed solutions is that we may take advantage of low utility rate during the off-peak hours, which is nighttime, and try to run backup refrigeration system of the highway system if there's no sufficient heat from the thermal storage system. Okay, typically highway you have to have a thermal storage. If do enough heat, several days running, we can probably run these things during use the off-peak hours. And here is a potential project. Actually, our student a design project at URI is design such cooling storage, ice storage, air conditioning. And here's an example of the utility rate in the year of 2008 at the New York City. And here is highlights, okay, particularly the peak hour, okay, which is defined as 12 o'clock noon to 7 o'clock, which all the air conditioning is on, is about 18 cents per kilowatt hour. During the off-peak hour, okay, it's a little bit more than 1 cent. Again, it's defined as 9 o'clock to 10 o'clock in the morning. You see the huge price difference right there. This is a year 2008. Okay, but nowadays the electricity, there's still some huge difference, probably more than triple, or the price is more than triple, but it's not as big as this now. The reason is that we have improved it, grid system, okay, smart grid, so we don't see this kind of huge difference in the price now. The idea is that we can build ice, run air conditioning in the off-peak hour, and off-peak hour has a better conditions, have lower temperature, is more favorable to air conditioning system. You can build ice or build cold storage there, and during the on-peak hour, you stop use electricity, but rather release the heat storage. So that's a potential method we can solve that. Okay, I'm speak a little bit faster. The third method, jump too quick. Okay, third method is that we can use the summer latent heat storage for winter de-icing. And many experimental highway thermal storage projects already done in the world. You can see all the website. People storage hot water into the ground, and in the winter time try to use a de-icing, particularly bridge. Here we propose, okay, we not only storage the hot water, that's not enough. We also should use the latent heat. Okay, latent heat is that similar to some similar to the ice, but it's not ice. Okay, some special material, you melt it, and that's have a more heat storage than the typical sensible heat. And this will be, there's many advantages. Okay, I list many advantages, and that can basically you can increase your storage capacity, and if the volume is limited. So let me talk, those are the typical storage material can you have. Okay, this is the solid material can you have, and also talk about cost. Talk about cost of this, use this phase changing material. Okay, this is the method, it's my favorable method, is use the winter cold energy storage for some applications. It is also noticed that the snow and ice is a form of energy in nature, but these have never been received their due attentions. Okay, people typically talk about energy; they never pay that much attention. But here is the things we can do, and snow and ice, okay, really creates lots of problems during the winter time. You have de-icing costs, you have environmental cost, and there's lots of potentially cost right there, and a few projects have been done now, but we somehow can do this. Okay, so here a list of these advantages. Okay, we have 7 different advantages. Let's say if you can collect and store the snow on the highways, and then in the summertime, used for winter, for the air conditioning, and that will benefit our living condition in many different ways. Okay, economically, environmentally, and also from the highway safety, all kinds of benefits are there. And this is a typical two method we can use, and for the storage of ice. Okay, when it's a centralized storage, when it's along the highways, and a more distributive system. So here is give you a cost of a storm storage. The example is that a small office building and how many space we needed for this ice storage. There's also issues and problems about that. So I'm going to skip this part. So lastly, I'm going to talk about design considerations of all these systems. And this is a typical model of the heat transfer model there. Heat transfer is a radiation heat transfer, conduction heat transfer, convection heat transfer. So from different angles, okay, first, this is a heat exchanger, but it's not different from a traditional heat exchanger, highway system. So those are the things we have to consider. And from radiation point of view, okay, we can build installation a radiation reflector. So reflect heat onto the highways because you want to collect the highway heat. So you want to reflect it back to the roadside. So this is the one thing we can do. And also, can we coat the surface, okay, to create the greenhouse effect? What happens is that you simply coat the surface, then you basically maintain the heat, preserve the heat. Okay, don't let heat go away. So this time you try to use as much greenhouse effect as possible. Okay, the third one is a model, theoretical model. Typically, people use a model as a gray body radiation, but in reality, it's not gray body. You have to consider those facts. From conduction point of view, and you can use a high conductive highway materials. That heat certainly conduct to the heat exchanger, but you also want to use a low conductive pavement on the basement. You don't want to, on the base, you don't want the heat escape to the soil, ground, okay? And also you talk about the structure. Can we use a superconduct structure like a mesh, build the steam mesh and into the heat exchangers so that heat quickly conduct to these heat connectors. Okay, I think that's my time's up.
Great, thank you very much. Because I promised to you everything will be done by 3:30. For 3:30, the social hour, we'll have two more presentations. Tommy is still here, okay? Because it's energy harvesting. Thank you, Professor Deng. I will suggest Tommy will do first energy harvesting, and then we save the best to last, okay? All right. Then everything will be done 3:30. Then we'll move it to the Universe Club, and then we'll have a social hour. You guys will miss the social hour? Yeah. Oh, you're right. Okay. Thank you for coming. Yeah, okay, great.
Hi, my name is Tommy, and my topic is on comparative analysis between rigid and flexible solar panel. So, just a quick question. I don't need an answer. Just how much do you think the government spend in sustaining street lights every year? All right, the motivation to my topic and why I chose this topic over the summer was because I figured that there's ways to harvest solar energy. So there's different ways. There's using the hot water in pipes. There's using solar panels. There's using asphalt from the roadways. But I was more interested in the solar panel one, so I picked the solar panel. And the whole motivation was to analyze between a rigid solar panel and a flexible solar panel. So the current status of this is certain PV cells, which are pretty much the solar cells, started in early 1740s, but recently it's been much more, seeing more usage in society. It's more acceptable and there's more knowledge of it than 1740s. When it first started, rigid solar panels was much more used for houses, but now they're going to street lights and highways and other infrastructures. All right, this is a picture of a street in New Jersey with a rigid solar panel on top of it. It's pretty good because it saves the government or the state government a lot of money in electricity bills going towards the light poles, and just it's pretty good for energy. If you guys are like go green and whatnot, it's pretty good for it. All right, so the government spending, the government spend about tens of millions of dollars every year in streetlights and just maintenance of it, of getting new ones or getting the light bulbs in it changed or getting the cover around it cleaned out. So the future plan is the government recently granted about $6.3 billion in stimulus money for energy efficiency stuff for highways. So the whole plan is to try to get this solar panels, the better one, implemented in this bill also, so to save more money and more money comes back to the state, whatever state implements it. All right, like I said, the payoff is just education. Whatever money we usually spend on solar panels could be used in the state for various usage. So like education, like the engineering building, employment, and also it's pretty good for the environment, for the ecosystem and stuff like that. So it's clean. So the objective was, this summer I was giving a grant from the College of Engineering to get 2 solar panels, a rigid and a flexible one, and to find out which one works better. I'm still working on it right now, so I don't have data to show you guys exactly which one works better. But so far, it's the flexible one. The flexible solar panel, they cost quite a lot compared to the rigid, but they're better in the long run. They're much more better to use. They could store more sunlight, more energy usage to go out of it too. So it's pretty better. All right, so to my right, which is that one, that's the rigid solar panel. It's just in a casing of a glass, laminated glass. It's not going anywhere. It's stationary. And the flexible one is pretty exactly what the name is, flexible. So it's pretty flexible. It takes the shape and object of whatever you put it around or in it. So a rigid solar panel has been known to have a little efficiency, but it's still enough to work to do the job. So with this research, we're trying to, some state, especially New Jersey, have some street that has flexible solar panel, rigid solar panel on it. So our goal is to take those rigid solar panel out and put a flexible solar panels in place of it, because a flexible solar panel could get sunlight from all angles during the day, while a rigid could get angle from one angle. And I know some people have questions about why don't we create a new technology to kind of rotate the rigid solar panel every hour or every 2 hours or so by so much degrees. We could do that, and there's actually a company out in California that came up with it, but that's more money added to the solar panels that we don't need. But we could just avoid all of that by just installing the flexible solar panel, and that does the job and less money. This is what my parents look like this summer. So up top is the rigid solar panel. It just stimulates it being put on top of a street light, and the 2 front ones are the flexible ones and just kind of wrapped around the pole to try to stimulate it being used in the highway system. All right, so when we connected those, when we put this Paris on the roof of Bliss Hall, we connected it to 2 5 watts light bulbs to kind of get the readings of it, figure out it works. So the more understanding I get of it now, I could get bigger solar panels and make the project bigger for the College of Engineering. So the 2 light bulbs, the rigid one goes to it goes to one light bulb, and the two flexible ones are connected. These two flexible ones are connected as one into one light bulb, and also produce its own light. So based on the reading, there was a meter and a timer that tells me exactly how much of the electricity was produced to the light bulbs, and how much came out, how much voltage coming in and out of the system. So, and based on the results, it came out that the flexible lasted longer than the rigid solar panels. And that's what the schematic looks like. So we have the two flexible ones. It goes to a to a charge controller, to the battery banks, and then to the light bulbs. And it's same thing on the rigid. This is just a picture of when it could be used in the highway system. I'm not gonna go too much into details of that. So the future plan is, ignore this. I kind of couldn't find a picture that has a rigid solar panel on it, but this is a street on highway in Africa, and it has solar panels all around it. And our goal is to get that implemented into America, into the United States, because it could, make us better, make us look better. I overheard the dean this morning talk to me, and he said, in Germany they have a very great highway system. Our goal is to make ours better. And just other stuff with that. Just to say thank you to the College of Engineering and to Korea Express Corporation. It kind of funded me to do my research, and I'm still working on it right now. So hopefully, when I'm done, I could get them their results and stuff. And that's about it.
Okay, so since it's still an ongoing project, next year you can make a real good one. So at the time, there'll be more question and comment. Okay, so yeah, you have one question? Yeah, I'll entertain.
Have you looked into 3D solar panels?
3D?
3D, yeah, like you have a solar panel that is it's either a monocrystalline or a poly. Is it?
Uh-huh.
Mono and poly. But, they have they're starting to develop these solar panels that have these ridges, whether they're carbon nanotubes to absorb some sunlight into the solar panel. But there's these ridges that actually extend up above the crystal structure and can absorb a lot more sunlight. So you should start looking into that.
Okay, definitely. I didn't think about that. Oh, I didn't really know about that. But okay, thank you.
I just have one question.
Yeah, please.
Under voting for 4, we're going to vote for 4 for the URI Engineering program. Do you think we could build a semicircular building so that they, if you talk to the architects, they can build a semicircular building that you can cover with
Flexible solar panels?
yeah.
Wow. That's great. Thank you. Good suggestion.
Thank you.
So Tommy, you got 2 gentlemen now work with, right? And then you got over to the that's your drink, right? All right. Thank you. All right. Okay. We save, as I said, we save the best last, as you know, right? So Laura Shipman, Dr. Laura Shipman.
Almost.
Almost there, right? We'll talk about environmental project. Okay.
Yeah, thank you. So I first of all want to acknowledge my co-author, Varun, who's sitting in the audience, along with our graduate, Ryan Sullivan. He's in the geology department. And then our supervisors, Tom Boving and Vinka Craver. We've been working on this project for a few years now, and we're basically trying to improve stormwater filtration because there's a lot of really nasty contaminants in stormwater, and we're trying to get a handle on how to improve the filtration so we can actually reuse the water that comes out of the filtration. So I want to give a brief overview of the talk. I'll start with, where does stormwater come from? What's so bad about it? Problems that are generally associated with stormwater. How do we manage stormwater, and how do we really do it in Rhode Island especially? Because there is something special about Rhode Island. Not that it's just small, but we also do a really good job about managing stormwater. What's an approach to enhance treatment options, and then how did we go about our laboratory project, to test materials and really implement them? And, final field implementation that's currently going on. at the Rhode Island Stormwater Demonstration Facility, which is right in one of the parking lots at URI. To go along with it, I have sort of a little bit of an outline down here to keep you, if you doze off or something, you can just check one of the boxes. They'll be highlighted to know where you are. Okay, so where does stormwater come from? Stormwater is anywhere it rains. So if you have a substantial rain event, you will get any sort of pooling on the surfaces or any sort of overland flow. And that's nothing, that shouldn't be surprising. What might be surprising to you is that there are a lot of contaminants associated with that. And they come from cars, from animals, from agriculture, anywhere. I mean, there's a bunch of different sources that accumulate on the road surface, and then when it rains, they get flushed into surface water bodies, estuaries, rivers, anything that you can think of, and as a result, contaminate them. And you can see that there might be some sort of algal bloom here. It could be bacteria that get flushed into there as well, resulting in beach closures and fishery bans and such, especially something that we encounter in Rhode Island, and that's all coming from impervious surfaces like roads. So if you look at stormwater concentrations in an urban area, you can generally find these concentrations right here that I've outlined. That's micrograms per liter. Doesn't sound like a lot, but they're actually toxic, especially some of these heavy metals are really toxic. You've probably heard of lead being very toxic. A lot of organic contaminants are very toxic. We focus on PAHs, which are polycyclic aromatic hydrocarbons. It's a big word, but they're carcinogens actually. So they're really bad. For reference, I have the maximum contaminant level set by the EPA here also. And just to give you an idea of, where we stand when it comes to stormwater runoff. And the values that are bolded are ones that commonly exceed drinking water standards. Not that anyone wants to drink stormwater, but it just is supposed to give you an idea of, what sort of concentrations we're talking about. So, now that you understand that stormwater really has a big impact on the environment, again, water quality gets decreased. There's a change in biodiversity that comes of it, and it also has oftentimes can lead to stream erosion and increased flooding, of course, when you have strong rain events. So I have this map here, and this is actually the Narragansett Bay watershed. So Providence is basically that yellow area, and the way this map works is that the green areas are generally areas that have low percentages of impervious surfaces, so forest lands and such. And then with increasing color, especially that yellow, that's where urban areas are. So Providence, think, really dense population. And then the red is Narragansett Bay, and those are impacted waters, the red colored waters. So you can really see that there's a strong change in water quality resulting from these high percentages of impervious surface. And that's related to stormwater. So in Rhode Island, we actually, in 2010, just had a publication from the Rhode Island Department of Environmental Management where they outlined different procedures on how to improve stormwater runoff or stormwater management, really. And it was there were 11 standards and performance criteria selected that reviewed how to incorporate stormwater management into low impact development. Really, and they also set minimum standards for water quality, and this is actually the only state in the United States that has some sort of water quality standard associated with it. Not even California. Everybody always thinks California is ahead of the game, but in this case, we really are ahead of the game, which is kind of exciting. So this is Rhode Island. You're all familiar with it. We are here in Kingston. What is this thing here? And we installed the Rhode Island Stormwater Demonstration Facility last summer. We started serious construction. And the idea is to amend and test materials that can improve stormwater filtration, and with that, we can evaluate the performance of enhanced materials that we could use in filtration practices in the field. So this is our whole objective, is to improve stormwater filtration. How can we do that? So one of the technologies that we're looking at is called a tree filter. And this is sort of a schematic of one. And a tree filter is basically a subsurface filtration system where the water from a parking lot structure or similar or a road infiltrates up here through grate and then percolates through some engineered media down to the ground. It could go directly into the groundwater. It could also get collected into a drainage pipe and then get discharged into a further treatment plant or a surface water body. But the idea being that once it's gone through this filtration system, that the water quality is much higher and as a result is safer to discharge than it is if it's untreated. So again, it's a subsurface biofiltration system. So when you buy these tree filters that run about $10,000 or so, $10,000 to $30,000 per unit, they usually come with something with the engineered media in it that it's a sand shale mixture, and that's what is commercially available. It's cheap and it works for the most part. These tree filter units are meant for urban areas, parking lots, roads. There's a bunch of them in Boston and Providence already actually, and they treat up to half an acre, maybe 3/4 of an acre, if you put them in succession of one another. So each unit treats about half an acre to 3/4 of an acre. So I was talking about the sand shale mix, and this is just an image of the expanded shale that we've been using that comes in the tree filter and that we've also been using in our experiments when it comes to material amendments and testing different materials to improve this filtration unit. So how can we make this better? Talked about all these contaminants and these tree filters. So if you have a conventional tree filter with this sand shale mix, it is limited to about 80% of total suspended solids removal. Total suspended solids is TSS. And the idea behind that is that a lot of contaminants attach onto particles and as a result might get pulled out if there's a really high removal of these total suspended solids. But what happens to contaminants that might be in the dissolved phase, or bacteria that don't necessarily always attach to particles right away? This current filter media that we have doesn't really address dissolved phase contaminants or bacteria. And more importantly, really, a lot of stormwater best management practices they've been testing bacteria removal, but it's very unreliable. It can range anywhere from 0 to 80%, and that's a huge range that really doesn't get us anywhere, especially if a 0% removal, that doesn't help you. And a lot of times the problem also is that if there is some sort of removal, the bacteria don't necessarily get killed or inactivated is how we like to say it. So they're still attached somewhere and floating around and could pose a potential problem. So we've been working with a wood-based filter matrix, and we're using red cedar wood actually. And the reason we're using that is because it's cost-effective and it's already been shown to remove organics and inorganics such as heavy metals from stormwater runoff. And we're hypothesizing that it can remove pathogens such as bacteria as well. So this is our red cedar matrix, and we got this from a local wood distributor. Again, it has a high affinity for organic contaminants and heavy metals. And then we used antimicrobial agents. So this is where the really exciting and innovative part comes in. So we used one type that's silane quaternary ammonium salt. Down below is the actual chemical name of it. If you want to look it up, please note it down. I'll give you a minute. And it works through actual piercing of a cell membrane. So it has this long carbon chain that you see that's sticking up to the top here. And if it gets in contact with a cell, it actually pierces the cell and deactivates bacteria. And this has been shown in other studies. The company that's developed this product, has done extensive work on this. So, and we've observed this in the laboratory. This works, which is really exciting. We used another antimicrobial agent, which is silver nanoparticles that we've made in the laboratory ourselves. And they work on a concept where they release silver ions from the actual particle that also attack the cell, and then cell lysis happens, the cell breaks, and the DNA gets destroyed. So the benefit of both of these antimicrobial agents is that they both have a positive charge. And that's important because generally bacteria that we encounter have a negative charge on the cells. So they actually already there's some sort of attraction between these two. So the bacteria get drawn in and get killed. Just what we want. So, how do we make this better? Well, we can amend these red cedar chips with either the TPA or the silver nanoparticles. And that's exactly what we've done in the lab. So how do we do that? We submerge the wood chips in a solution containing either the TPA or the silver nanoparticles and absorb on and load the antimicrobial onto the wood chips. We test this, we just test the stability to see how long it stays on there, whether it stays on there in the first place, and to see, how this works, if this is something feasible. And you always have to keep in mind that the shale is always there as a base comparison, because that's what's being used in the conventional filter. We're trying to improve it, so that's our 0.0 comparison, so to speak. So everything that we make, we compare to a shale performance. So now that we said we amended these materials, and these are our loadings that we've achieved. So for TPA, I'm going to give an example. We put 3.6 milligrams per 1 gram of wood chip. 3.6 milligrams of antimicrobial per 1 gram of wood chip onto, that's our loading. So similar with the silver nanoparticles. And we tested contaminant removal, heavy metals, organic contaminants. And then we really also wanted to see, does it work for bacteria? And we used E. coli for a couple of reasons. One, E. coli is very intensely studied, and it's also the regulated organism in stormwater. So I was showing you and telling you before that we amended these wood chips, and this is what we got. I wish this pointer worked, but it doesn't. So on your left, we have the TPA, amended wood chips, and then we have shale also. Shale is in gray, and TPA is in lighter gray, or white, so to speak. So, and a similar picture for silver nanoparticles on the right-hand side. And you can see already the bars for the wood chips are much taller. That just means that the wood chips have a higher affinity for both of these antimicrobials. So they can achieve a higher loading, they can hold on to more antimicrobial. When you look at this graph, there are also bars that have a crosshatch pattern in them. And those are pretty much the same size as the bars that don't have the crosshatch pattern in them. And that just means that there is absolutely no desorption, meaning that everything that we put on from these antimicrobials that we load onto the wood chips does not come off, even if you put it into water, up to a week, even 120 days we tested this. So it just doesn't come off. Thank you. So
Same problem?
maybe it's me.
Oh,
It's okay. Don't worry. Don't worry.
Yeah.
It's all right. So the values here on the bottom basically just tell you or show you what I just told you. So there's very little desorption. So this shows us that the antimicrobial enhancements absorb very strongly, and they would not be released into the environment if we were to put this into a tree filter system. So to continue on, we tested these different antimicrobials in different concentrations, and we wanted to see, all right, where can we take this? So we picked 5. We actually picked a total of 6, but this one of them is not listed on here, and continued experiments with those. So the ones that are in boxes are the concentrations that we picked to continue experiments with. So we talked about metal removal. We wanted to just see what happens if we amend these materials with our antimicrobials. How can we impact is metal removal impacted, or is it getting better or worse? So we looked at these 5 different metals: cadmium, copper, nickel, lead, and zinc. And this is what we got. So you have lead, cadmium, copper, zinc, and nickel, not in the same order, but they're there. And you have shale always as a base comparison. The line is black for shale. And then the red cedar, that's just red cedar all by itself, is in orange. Any modification with TPA is in green, or darker colors signify higher loading of TPA, and the same idea goes for silver nanoparticles in blue. So you can see that with a higher loading, you generally get higher removal, and this is particularly true for lead, which is one of the very nasty, commonly occurring contaminants in stormwater. So, and this is pretty exciting, especially because compared to shale, there's really no, you can't even, of course we are comparing them, but even just using wood is much better than just using shale, which is used in the conventional system. So that's pretty good. And we modeled this using a common absorption model called the Langmuir model, and this is what we used. I'm not going to go into great detail, but it basically, there's a set of experiments that you can conduct that gives you values to plug into this formula, and then you can get a maximum absorption coefficient, which is Q, and that's exactly what I've plotted on this y-axis here. So that's increasing with higher loading. Looking at organic contaminants, we selected PAHs, polycyclic aromatic hydrocarbons, and we modeled it using the same equation. And again, you have on the y-axis, you have the maximum absorption capacity for these two compounds, asenaphthene and fluorine. We picked those as representative PAHs because they're pretty soluble compared to the other ones. And the same trend. You're probably wondering, where's shale even on this graph? It's there. You just can't see it because there is no absorption. There's no removal from the aqueous phase using shale for these pHs. So that's pretty exciting. So you can really see that using these, even if these antimicrobials don't just act as antimicrobials, they also act as enhanced absorption for organic contaminants. So yeah, this is it. If we just use red cedar, we can get up to 35 times higher removal compared to shale. That's pretty exciting. Okay, so that's good, but we're really interested in bacteria removal. So very similar idea, we used E. coli again. So on the x-axis, we have the different materials that we tested. And on the y-axis, we use something that's called the log removal value. Because bacteria occur at really high concentrations, ranging orders of magnitude. We have here, we're starting at 200 going to 1 million coliform forming units per 100 milliliters. You use log values to give an idea of what the removal is. So anytime you get something over 2, it's pretty good. So you can see that when we have these really high loadings of 6 TPA and 9 TPA, 6 TPA being 6 milligrams per gram, and 9 being 9 milligrams per gram of TPA per 1 gram of wood chip. And even the silver nanoparticles are doing really well at removing these bacteria from the aqueous phase. On your right is the natural decay, which is just the normal removal, or well, not removal, but it's the amount of bacteria that just die in a controlled solution that are not exposed to antimicrobials. And again, shale is all the way to the left, not doing very much, not removing very much. So again, we can remove up to 99 to 99.9% of bacteria, and that's commonly what you see on household cleaners. If you think of Lysol to clean your bathroom surface on those wipes, it says 99% removal. That's exactly what we're getting using 1 gram of wood chips for 25 milliliters of water. So that's a pretty good ratio. So this is all done over 3 hours of time. So now we're looking at, what can happen if we do something over shorter periods of time. Sorry. So something called the Chick-Watson model, which is commonly used in wastewater disinfection. And what we did here is we tested, again, the bacteria removal over different time periods, 30 minutes, 90 minutes, and 180 minutes. And then we plotted it on a graph, the same way that we did before. And the higher the modification, the better the removal. And the slope is steeper too. And the same goes, when you add silver nanoparticles into the graph, it follows the same trend. And basically, we parameterized the model, and we found that the following models for the two different antimicrobials. And basically what this means is that if you have an N, which I don't know what happened to the rest of my parameters, but the N that's raised, so C to the N, the concentration, the C, N is the coefficient of dilution. And basically that means if the N is greater than 1, concentration of the disinfectant is very important. But if it's smaller than 1, and is smaller than 1, then time is much more important. So we found that for TPA, the concentration is much more important for removal compared to silver, where the time is much more important. For TPA, concentration is more important. For silver, time is more important. That makes sense because it relies on silver ion release. So we're trying to confirm that these things are actually, that these bacteria are being killed. And we're doing that by looking at scanning electron microscope images. And you can see in A and B, that's unmodified red cedar. That's just no antimicrobial applied. And the bacteria are in good shape. They look healthy and happy, and they look like they are supposed to look. Whereas in C and D, you can see that they got destroyed. Their cell membranes are punctured. And that's confirmation that our antimicrobials are working. When you compare this on a cost, for a cost-benefit analysis, again, a tree box filter costs about $10,000. If you add some red cedar wood, it's about, maybe up to $400, about a foot. Not a lot of money if you think about spending $10,000 in the first place. If you add then the amendments that we talked about at the level that we would recommend, you get about $5 to $6 increase per pound for TPA versus silver nanoparticles, which are much more expensive. And you end up with an overall cost increase of less than 8% using TPA compared to silver, where you accrue a cost increase of about 30%. And as a result, we recommend using TPA as a amendment for filter media, and it's just more effective. It's more effective, and it's just also cheaper. So when we test this in the field, we, I told you that we're testing this at the Rhode Island Stormwater Demonstration Facility, which is at URI, and it's one of the parking lots that's right north of the campus. So what we did is had two of these two filters put in. One is the conventional system, and one's an innovative system, because we want to compare them. So we have one that has just the engineered matrix using the shale and the sand, and one has our matrix that has an added 30 kilograms of TPA, modified wood chips. And we're sampling stormwater influent and the effluent every week. And we've been doing this since November. So what we measure is the influent, and you can see here in this image, there's from January 27th, there was a very intense rain event, and the filter just was completely overwhelmed, and it flooded. So that's what happens, and that's okay. That's fine. The water just sits there, and it'll infiltrate through the ground. And what we actually have set up is that we have a sampling pan set up at the bottom of the filter, and we can pump the effluent up to the top coming out of that black tube, and we can then analyze our samples. So we can see what's coming in and see what's coming out, and then we can see if there's any difference in between. So that's what we've been sort of doing for the past year. A lot of that data is still, we're working on it, so not too much to report yet, but it's been going on and we're testing. So if anyone has questions, I can give you a little bit more of a rundown of this at the end. So basically what we found is that using modified red cedar is much more effective at removing dissolved contaminants from stormwater in addition to bacteria. And that this TPA modified wood is much more cost effective than using silver nanoparticles if you're thinking about adding that into a stormwater filtration system. And that's it.
Great.
Thank you.
Excellent. She had wonderful presentation. She doesn't mind taking a couple of questions or
No.
comment, right? If you have.
Absolutely.
Yes.
How long do wood searches last for?
How long do they last for? So they're actually very resistant to degradation. There's been, people have found cedar trees, fallen cedar trees in swamps that were 12,000 years old and didn't degrade at all. So it's very resistant to degradation.
What about for like the bacteria, like over time, the degradation of the bacteria that is amended on those wood searches?
What happens to them?
Yeah.
It's fine, nothing. They'll get flushed out. So they should, there shouldn't be a problem. Because if they're dead, they're dead. They're not gonna do anything.
All right.
Yeah?
Any other comment, question?
Yeah.
Where
Yeah.
is the URI stormwater demonstration facility?
It's on the parking lot on Flag Road. It's the Flag Road parking lot.
Oh, it's bottom of the,
Yeah, it's not the one all the way to the bottom of the hill. It's when you're going down. It's the one on the right-hand side. Yeah, so there's a little shed set up that has electricity, and so we can actually conduct experiments there. Yeah.
Okay, great.
Yeah.
Thank you again.
Thank you.
Right. Thank you for your staying late. The students have different schedules, so they are come and go. But the last time when we count was 125 restoration. So I thought that this is the way we can have action among not only faculty and students, the consulting engineers, contractors, politicians, citizens, something like that. Once a year, we are using this one as a extension of classroom. However, this is the end of the day, so now we need to think about where we go now from here, right? We talk about, okay? As a transportation engineer or transportation professional, I think we should provide the public strong, sustainable transportation infrastructure such as road and bridge. Same time, we need to also provide good public transportation, as we heard from Amy Patton during the lunch hour. And also, there are all different modes of the transportation. I think we need to optimize those modes together. And then, as you know, our challenge very soon, we're actually already here. The energy is not unlimited, especially the fossil oil. And then we need to work on how we can, conserve, those energy, or how we can explore new alternative energy, etc. Those kind of things I think I'm hearing throughout this forum. You have any other comment overall how we can go from here? The one more thing is I invited the person who is in charge of research, Mr. Colin Franco, but he did not show up. So I don't know what they have in their mind, but maybe we can check later. So I think we have to work together, but in some reason there is some sort of disconnection recently. Which I never experienced. I had a really wonderful relationship with all the DOT directors except current one, but I hope the new election will get a new governor, and then maybe things will be changed. So hopefully the state university, state DOT, you know, consulting firm, and then contractors, citizens, politicians, we need to work together. How we can serve better the public through providing the sustainable, environmentally sound transport infrastructure. And that's I have in my mind. Do you have any others to talk? If not, you know, as I said, the Universe Club prepare whole day, the social hour, so you can move to cross the street, and then let's talk more over there. How they sing. Okay? So with this, I would like to adjourn the 27th Rhode Island Transport Forum. Thank you.